In this problem, we are told that a archer in the great old medieval times has a bow, and he shoots an arrow of 90 grams, and it travels at an average force of 110 newtons on average throughout its travel. The total displacement is 79 centimeters to the target. Assume that there's no change in y and that arrow travels perfectly linearly through space. So we are asked, what is the speed of the arrow throughout the travel? So to solve this, we need to understand what kind of equations we're working with. I see a mass, I see a force, I see a distance. Okay, force times distance is what? That's work. We know that work is equal to a parallel force times the distance of which you travel. We can also say that if we're trying to use work here to solve for velocity, well, work net is equal to change in kinetic energy plus change in potential energy. And we know that kinetic energy factors in velocity by saying that 1/2 mass velocity squared is equal to the kinetic energy. Okay? So we're going to use these equations here to solve for the speed of the arrow when it exits the bow. So our potential energy here, I want to make a point. The work net is not always equal to change in kinetic energy plus change in potential energy. And I say this because, well, if you think about it, is the potential energy changing? No, not really, right? Because if you think about it, if the arrow shot here and ends up here at the same height, no change in height, what happens to potential energy? Potential energy is mass, gravity, height. Mass and gravity are always constant. It's a 90-gram mass. It's pointed towards the Earth, negative 9.81 meters a second. But the height can change, and a change in potential energy really just depends upon the changes in height, right? That's why we say that potential energy is is energy based on your position, right? If I'm at the top of a hill, I have more potential energy than if I was at the bottom, right? We'll assume that this is 0, right? So height does not change, right? So what happens to the change in potential energy? It goes to 0. Okay, so that just drops out of our equation, and we are left with that the work net is equal to the change in kinetic energy. So I also want to make another point here that will help us solve. We say that the work net is equal to the change in kinetic energy. But what is the overall work of the system, the sum of the work done on this arrow? Well, it's quite literally just equal to that, right? It's a force times displacement. There's no other weird work being done on the arrow other than the force it was given by the archer's body, right? So we can say that this is also equal to work net. That the work net is equal to that force times displacement. So we can make a relationship here, which is important. We can say that the force in the parallel direction times the distance is equal to the change in kinetic energy, which also simplifies to the parallel force times distance is equal to 1/2 mass velocity final squared, right? We're taking a difference, a change, 1/2 mass velocity initial squared, right? We have our final velocity minus our initial velocity, and then factoring in the 1/2 mass part and squaring our velocities, right, to give us kinetic energy, right? And remember that change is final minus initial. Okay, fair enough. I think you get the point. Let's move on. So I want to simplify this so it's not such a pain in the butt to think of. Or actually, I have an easier simplification. What is the velocity initially? So let's assume that the final velocity in this case, you can think about it either way. You'll get the same answer, you'll just get an opposite sign. Your final velocity, before you shoot it out of the arrow, it's 0, right? 0 meters a second, because the archer's holding potential energy in his arm. He lets go, and it's from elastic potential energy, right, which you'll learn about in the springs. But we have that potential energy. It's stored into kinetic energy, which then allows the arrow to go. So initially our bow arrow is moving at 0 meters per second. Okay, what do you think it does to this term here? Okay, if I were to plug in 1/2 mass and we put in our velocity of 0 meters per second and we squared it, we get 0 squared is 0. Mass times 0 is 0. 0 times 1/2 is 0, so this whole term is 0. Therefore, it does not matter. We're not subtracting by anything, so we are fair to say we can just drop it out of the equation. It just grew legs and ran away. So this here is our equation to solve. Now let's actually solve it. So the force in the parallel direction, we know to be 110 newtons, times the distance of which it travels, 79 centimeters. How many meters is that? 79 centimeters, 100 centimeters over 1 meter. That is 0.79 meters. So we know that we can just do 7.9 meters. We get joules when we multiply. Newton meters is a joule. 1/2 mass, and our mass is 90 kilograms. We do the same style of conversion here, and let me bring the camera up just a tad. 90 grams, we know 1,000 grams is equal to a kilogram. So we do the simple math here. We get that we have a mass of 0.09 kgs. So we can actually plug in here, and we can actually go ahead and take this one step further, just have the mass to simplify 1/2 mass, and we can get 0.045 kgs, okay? And that's equal to velocity final squared, okay? So let's now bring over kilograms, right? This is going to give us, if this is in Newton meters, this is going to give us meters squared per second squared, right? Because newtons is kilogram, meter, a Newton meter is this, over a kilogram. These cancel, you're left with this. We'll take the square root of this because, as we'll see, and we'll get meters per second. So let's go ahead and do that. We've established the game plan. So times 0.79 divided by 0.045. We have 1931 meters squared, seconds to the negative second equals our final velocity squared. What comes next is just a square root. So we take the square root of our velocity and we get our final velocity is equal to 43.9 meters per second. And again, I'll just say this. We got our final velocity. Does it make sense? Right, so our initial velocity was 0, and it shoots off. It turns all that elastic potential energy from the archer straight into kinetic energy, and the arrow starts to travel with some velocity, and that velocity is 43.9 meters a second. I hope you learned something in this video. If you did, please like, subscribe, comment if you have any questions. I'd love to answer them. Have a wonderful day, guys. I'll move out of the way so you can look at the problem just in case.